Conservation principles. The most powerful concepts in science are called conservation principles. These allow us to solve problems without worrying too much about the details of a process. We just need to know where it started and where it finished. We just have to take a snapshot of a system initially and finally. By comparing those two snapshots, we can learn a lot. If we're analyzing a traffic light, the only important thing is where it started here, especially if we're driving, and where it ended up here. So we just need to know it started with green and wound up red. Don't care about the electricity in it or if it passed through any other dimensions, just care about the beginning and the starting point. Energy is a conserved property of nature. The law of conservation of energy states that energy is neither created nor destroyed, and energy can only be transformed from one form to another. For now, we'll talk about energy being conserved on its own. Energy is neither created or destroyed, and energy can only be transformed from one form to another. We've hinted at this before, but now we're going to put it in a little more formal basis. We have our work-energy equation. Initial energy plus work equals final energy. If we do zero work, then we have initial energy is final energy. That's the conservation of energy. Like the conservation of momentum, this is a law of the universe. Actually, the real law is the conservation of mass energy. The total mass and energy is conserved, and one can actually transform into the other, but you'll see that in more advanced physics classes. Here's an example of gravitational potential energy converting into kinetic energy and then partially back into gravitational potential energy. We have our little wheeled cart here, let's just call it a cart. It's on top of a hill and it's not moving. So all of its energy is gravitational potential energy. Then we give it a little push and then let go. Down at the bottom, we're going to use this as our reference point for gravitational potential energy. So all it has now is kinetic energy, and it's moving its fastest. Then it comes up on the slope, but not as high as it was originally. So it will have both gravitational potential energy and kinetic energy, but it will be moving slower here than it was over here. Here's another example of a gravitational potential energy converting into kinetic energy. Drop a basketball from the top of a door. So here's our basketball. At the top, it's 100% gravitational potential energy, and it's not moving. And somewhere down here, it has some gravitational potential energy and some kinetic energy. It's moving slow. Then at the bottom, right before it hits the ground, it's 100% kinetic energy, and it is moving fast. As the basketball falls, gravitational potential energy converts into kinetic energy. When the ball hits the floor, some of that kinetic energy converts into sound energy, some into thermal energy. The floor heats up a little bit. And then some stays as kinetic energy as the ball bounces back upwards. As the ball bounces back up, all remaining kinetic energy will convert back into gravitational potential energy until the ball comes momentarily to rest and then starts falling again.